We're going to look at algebraic expressions that involve powers of variables and expressions. So there's a single learning outcome, and that is learning how to deal with simplifying expressions that involve those kind of things. So expressions that involve powers of variables. As we saw in the first mini lecture, we repeat that theme that what we know about numbers extends over to variables and expressions. So a good place to start is just by recalling the rules of indices as they apply to numbers. So what we've seen with these rules of indices is things like the following, that 3 to the power of one number m multiplied by 3 to the power of another number n, we can calculate that by adding the powers. And we have good reason for this. This involves a product of 3 written down m times. This involves a product of 3 written down n times. So overall, we'll have m plus n powers of the number 3. Likewise, we're able to deduce that 5 to the m divided by 5 to the power of n is 5 to the power of m minus n. And from there, we can conclude that 1 over 2 to the power of n must mean 2 to the power of minus n. If we write down the same number to a certain power repeatedly, we would have structures like 7 to the m down to the power of n, and we can deduce just by counting really that that must be 7 to the power of m multiplied by n. I might just emphasize that by writing it out longhand. That's m multiplied by n. So the key point I want to make here is, well, apart from just recalling these rules of indices, the key point I want to make is that everything we see here applying to the numbers 3, 5, 2, and 7 applies not just to any number, but also to any base, which might be a variable or indeed an expression. So that rule of thumb will help us to simplify expressions involving such powers, so powers of variables. We need one other bit of information, and that is how to deal with a situation where we have expressions that involve different bases. And that's exactly what we have here. So we have here two different bases. We have powers of 3, and we also have powers of 5 that are being combined in various different ways. So the key thing to bear in mind here is that we apply the rules of indices to those two different bases separately. So if we focus on the 3, maybe I'll try and put a line around the powers of 3. We have 3 to the power of 2 over 3 to the power of minus 2. Put a different line around the powers of 5. Do I have? I have 5 to the power of minus 3, and that's divided by 5 to the power of 4. So I deal with the powers separately. So I've highlighted them there in different colors. So isolating that we have 3 to the 2 over 3 to the power of minus 2. In the numerator, we have 5 to the power of minus 3, and that's being divided by 5 to the power of 4. So we can apply our rules of indices separately to the different bases to conclude that overall the powers of 3 must be as shown. We have 3 to the power of 2 in the numerator, subtract the power that's in the denominator, following our rules of indices, and that's multiplied by 5 to the power of the power in the numerator is minus 3, and we subtract the power in the denominator, the 4. Tidying up, just by doing the addition and the subtraction, we see that we have overall 3 to the power of 4 times 5 to the power of minus 7. Okay, so the key point there is that when we have different bases, 3 and 5 in this example, we deal with their powers, we deal with their indices separately. And that's going to be important when it comes to algebra, because rather than 3s and 5s, we may have x's and y's. And the key point is that we'll deal with those separately, but using the usual rules of indices. So here's our first example, and it's exactly what we've seen there. So let's apply our rules of indices to simplify this expression. So really what simplify means here in this case is write this as a to the power of some number m multiplied by b to the power of some number n. Why would we do that? Well, it's because it will make the subsequent calculation easier for us. So our first thing to bear in mind here is that the numerator, a times b to the power of 3, well, let's do it at longhand. That's a times b multiplied by a times b multiplied by a times b. And the whole lot there is being divided by a to the power of minus 3 and b to the power of 5. Okay, so I kind of need to do a little bit of preliminary calculation with the numerator. Key point here is that when we're multiplying numbers, the order doesn't matter. A times b is the same as b times a. So I can multiply the a's together first. So I have a times a times a, which of course is a cubed. And then all of those are multiplied by b 3 times b cubed. And then that's divided by a to the power of minus 3 times b to the power of 5. So as we had in the previous example with the numbers, I can write down the powers separately. So what will I have? How many powers of a will it be? Well, there's 3 in the numerator, and I subtract the minus 3 that's in the denominator. The powers of b, we have 3 in the numerator, and we subtract the 5 that appears in the denominator. Tidying up then gives us our result. A to the power of 6, 3 subtract minus 3 gives 6, and b to the power of 3 minus 5, that's b to the power of minus 2. So there's our expression simplified. We collect together all the powers of a, all the powers of b to give us this much simpler form of that algebraic expression. Our second example here asks us really to tidy up this algebraic fraction here. So we have some numbers knocking around there, and we have different powers of t in the numerator and in the denominator. So what we'll do is ultimately tidy that up so we can write it as some number a multiplied by a certain power of the variable t. Okay, so let's start by just writing the expression as it originally appears. So we have 3 over t squared, and that's all getting divided by 6 over t. The parentheses, the brackets there are just kind of really keeping things together in a logical order. So 3 over t squared, well, 1 over t squared we know means t to the power of minus 2. So the numerator, I can write that as, well, let's break it down. That's 3 times 1 over t squared, and I might put in brackets there. And likewise in the denominator, I have 6 multiplied by 1 over t. What I can do next then is recall that 1 over t squared means t to the power of minus 2. And in the denominator, I'll recall that 1 over t means t to the power of minus 1. Okay, so now I can continue my calculation. I can keep the numerical parts separate. I have 3 over 6, and that's being multiplied by t to the power of minus 2 over t to the power of minus 1. Not really necessary to do that line, but maybe it makes things a little bit clearer. So I have my 3 over 6 multiplied by, and now I'll deal with the powers of t because I have minus 2 in the numerator, and I'll subtract the power minus 1 that appears in the denominator. So overall, where will this bring me? 3 over 6, of course, is 1/2, simplifying the numerical fraction, and that's multiplied by t to the power of minus 2, subtract minus 1, that gives minus 2 plus 1, that's t to the power of minus 1. And there's my result then. I have that written in the form of a number a, which is 1/2, times t to the power of minus 1. So I could go up and just record that answer there, that when we tidy things up, we find that a is 1/2, and the power k is equal to minus 1. Okay, so we're applying to algebraic terms there. The t in particular is a variable in this expression. We're applying the usual rules of indices to variables. Our last one now, looking a little bit more complicated at this stage. Again, we're going to simplify this to write it in a single expression with just one power of x, or a certain power of x, and a certain power of y. So we want to figure out what's the number a and what's the number b. Okay, so let's again start as usual just by rewriting the expression. So I have x squared by y cubed, then we have x cubed y to the power of 1/3. Okay, so the first thing that we'll do here is just sort out the second factor, the second part of this expression. And the way that powers of powers work is, well, we'll have x3 to the power of 1/3 multiplied by y to the power of 1/3. Okay, so what I'm using there is that for any numbers, variables, or expressions, a times b to the power of some number k, well, that's going to be a to the power of k multiplied by b to the power of k. We saw that a moment ago in the previous example when k was a positive whole number. We had a times b to the power of 3, and we realized that that's a to the power of 3 times b to the power of 3. This works for any number k, not just 3. There's nothing special about 3. So when I see x cubed times y to the power of 1/3. I can write that as x cubed, which is kind of like the a, times y to the power of 1/3. So I have exactly what I have in this general example, in this general rule of how indices work. That's exactly what we have here, with a equal to x cubed, with b equal to y, and with the power k equal to 1/3. Okay, so we can carry on now. So we have, well, nothing has happened yet with our first expression. That's just sitting there happily. Now I have x cubed to the power of 1/3. How do we deal with powers of powers? We multiply them. So I'll multiply 3 by 1/3 to get x to the power of 1. And I'm multiplying by y to the power of 1/3. And now what I do is I deal with the x's and y's separately. So I'll have x squared multiplied by x to the power of 1, and I'll have y cubed multiplied by y to the power of 1/3. So my result overall will be, we're multiplying all the way through here. So I have x to the power of 2 plus 1, and we'll have y to the power of 3 plus 1/3. So that will give us what? That will give us x to the power of 3 and y to the power of 3 plus 1/3. Adding those fractions, that will give us 3 to the power of 10 over 3, 3 and 1/3. Okay, so that finishes that mini lecture and those examples on dealing with algebraic expressions that involve indices, in particular powers of variable expressions